Okay, this tutorial is going to be a general rundown on the key components in the suspension system, basically all the parts you need to know before you start looking at the methodologies and any design work that you start. What you're seeing here is a cutout of our chassis, not the entire thing, just where the point's attached to. This is the front of the 2020 chassis with the key suspension components attached. So you're not going to see the details at the back middle of the car, but this is enough to show just what we need to know here. Starting off, we have the most obvious components. We have the chassis, which is the frame of the car that everything has to bolt onto. We have the tire and wheel. We have your actual shock or damper, whatever you want to refer to it here. And then these are the control arms. Now we're going to break down how this all gets assembled, how it all moves, how the suspension system actually functions. So first, you obviously have your tire and wheel assembly. This exists as a whole. This will rotate around on the upright. Let's move that back into position there. So those should be obvious. We'll get rid of these. Hide that. Hide that. Now, down to here. These are your lug studs, you can refer to them as. These are what the wheel bolts onto, and this is all part of an assembly called the wheel hub. So these studs run through all these plates you see here and attach to a hub, which is inside of this bearing, inside this carrier called the upright. This allows the wheel to spin freely around on this bearing when attached to these studs. So the next parts we're going to be looking at here, this is called a brake hat. Consider this all as one assembly here. This brake hat essentially allows us to attach a brake rotor onto the wheel hub. So the brake rotor is this piece here, which the brake is going to grab onto. This is what allows your car to stop. This is generally an iron disc. It tends to have the best braking material, not usually steel. Some teams use steel, but it does fracture much easier and doesn't offer as much stopping power. Cast iron is the most common component. So the brake rotor here, we can hide that as well now that we know that piece, which attaches onto this brake hat. And the brake hat itself just slides over top of the lug studs and gives you a mounting surface with these holes here that allows you to put bolts through to attach the brake rotor. This is a CNC aluminum piece. Has to be custom manufactured. They aren't what you would find on a production vehicle. Normally on a production vehicle, you'd see this hat and the rotor is all one piece, and it doesn't come apart in two sections like this. For our purposes though, we have to have a two-piece design like this. It's much lighter and allows us to use a smaller brake rotor. So we'll hide this as well. Now we're down to just the wheel hub itself, so you can see more what's behind it. These studs are pressed through the wheel hub, so there should be a hole underneath where the stud is. It gets press fit in, it's held in pretty much just by friction. There's some serrated teeth on it that allow it to grab in, and this is what your wheel assembly bolts onto. Because you have a nut on the other side clamping down the wheel, this also clamps into the wheel hub and you don't have any issues with these slipping out. That's why they're allowed to be a friction fit piece. And then to allow this wheel hub to spin, there is going to be a bearing on the other side of it. As you can see in this assembly, this wheel hub spins freely, allows it to move. There's a bearing inside here that it's press fit into. It's a very, very tight press fit. So it, generally speaking, holds itself in. Just as a backup though, we run a large bolt through it with a nut and a washer on this side that clamps down the wheel hub and bearing together and prevents the bearing from slipping out, or the wheel hub from slipping out of the bearing. So let's hide these. So get rid of the nut, get rid of the bolt, get rid of the washer. That's a washer as well right there. So now we're seeing just the wheel hub itself. And you can see this is where the bearing would be back here. Nothing's colored in, so it's kind of hard to tell. But if we hide the wheel hub, see that runs all the way through. Now we're left with just the bearing inside of the upright. Generally speaking, we should have a retaining ring that slots into this disc. It's just missing this assembly right now. This bearing is press fit into the upright. Once again, a very, very tight fit, so it holds itself in quite well. As a safety precaution though, you put a retaining ring into this slot, which absolutely prevents the bearing from backing out, gives it a wall to rest against. And you can see on the other side here, the bearing itself presses into a wall machined into this upright. So it can't move out to the right, can't move out to the left. It's absolutely stuck in there. Let's hide this bearing. Now we're left with just the upright here. So if you can see inside, there's that wall that the bearing would rest against. And then we put a retaining ring into this ring here, which gives it a second wall on the backside to rest against. And so now we are left with the upright and the brake caliper. It's the only parts we have remaining here. The upright is a CNC'd aluminum piece. This holds on to the control arms, which allows it to attach to the chassis, and this gives us a surface to mount the wheel package to, so the hub and bearing gets pressed into here, as well as the brake caliper gets mounted onto this. The brake caliper is just mounted on with a couple of lug studs, threaded ones, a very large thread, and this we can get rid of as well for simplicity's sake. Okay, we'll get rid of that. So now we're left with sort of the bare bones pieces. Now that we've gone through the wheel package, we have just the suspension components left. So what we're left with here is still a fairly complicated system. These joints up here, we have these V-shaped arms up here, another one on the bottom, same V-shaped design. These are referred to as the control arms. This is what attaches the upright to the chassis and allows the wheel to move up and down in an arcing motion. On the end of the control arms here, there is a rod end, another one there, same on the bottom, and then we also have a spherical bearing in here, similar to a rod end in function. It just mounts up a little bit differently. That is all bolted on the upright, and all of these joints are capable of pivoting on a 360-degree axis. It can go up, down, left, right, and that allows the control arm to have a smooth arcing motion. So we grab onto this and move it. Did I fix something? I fixed this. Yeah. Here we go. So we can grab onto this, and this allows us to now swing the control arm up and down through an arcing pattern. SOLIDWORKS is very glitchy with this, so it will jump around a little bit. This is what allows the wheel to move up and down through its suspension travel, is those pivoting joints on the ends of the control arm. Now, when you look at the car from the front view, notice that these control arms are not quite the same length. They are a bit different. Because they are different length, they will pivot on a different arc. The radius of the arc from this point to where it attaches to the upright is different for the upper and lower control arms, meaning that they can't follow, top and bottom can't follow the exact same path. So when you grab onto this and move it to a slight amount, the upright over here will change its angle of inclination. This is referred to as the camber angle. That is how far this upright is tilted in or out relative to a plane along sort of this direction through the center of the chassis here. So see if I can move this smoothly if SOLIDWORKS lets me. When we bring this down and back up, it is a very, very slight change. We're only seeing about half a degree of change, but the camber angle does change as the suspension moves because these have to follow different arcs. Depending on the length you make these control arms and also how far you space them apart and what angle they rest at relative to each other, your camber angle will change and your camber curve will change as it goes through the full arc. So you could have a very steep camber curve where it changes from like -1 degree all the way to -5 degrees. That's a lot of camber change. Or you can reduce this to a very small number like half degree or 0.3 degrees so the camber will remain fairly consistent through the whole motion. This is completely dependent on how you set this control arm geometry, what length they're at, and where they mount up to. And these control arms here are going to be made out of a few different parts. These are just metal rods welded together. Then we have the threaded inserts that allow us to put the rod end into. So this gives us a thread on there that this threads into. This is a lock nut that's used to hold the rod end in position. And then on the other end with the spherical bearing. This bearing here, it's a little bit hard to tell from the assembly. It's a press fit assembly again. And so this is a separate cup here that this spherical bearing gets pressed into, held in mostly by friction, but we once again put a retaining ring in it, much like we did with this wheel bearing here, to make sure it's held in place. Then this all gets bolted up to the upright and also bolted up to the chassis here. That allows us to have a smooth motion through our wheel travel. Now, the next part of the suspension is going to be this rod here. This could be referred to as a pull rod or a push rod, depending on the configuration you have it in. What this allows for is connecting this upright, or in this case it's connected directly to the control arm, but you want this mount as close as you can to the wheel itself. But it connects that whole assembly down to our damper here, or shock, whichever you want to refer to it as. Thus, when you move this control arm, it will move this rod as well and force this spring to compress. In a pull rod configuration and push rod configuration, you have to sort of think of it in opposite ways almost. This is breaking itself here. There we go. Get her back into position there. This last piece here is what allows for that motion to occur. This pull rod is attached there, shock is attached here. This is what we refer to as a rocker or bell crank, depending on which country you live in. Call it whatever you want. The end result is that it is a pivoting mechanism that translates motion from this pull rod into motion at this damper. There are a lot of interesting characteristics about this piece here. So first off is referred to as the motion ratio. The motion ratio is saying that for a certain amount of motion the wheel travels, so the wheel goes up 1 millimeter, 2 millimeters, you will see a different amount of motion at the damper. So a motion ratio of like 2.0 would be saying that for every 1 millimeter of wheel travel you have up and down, you will have 2 millimeters of damper travel. And then a motion ratio of 1.0 would be saying for every 1 millimeter of wheel travel up and down, you will have 1 millimeter of damper travel. And that travel is measured longitudinally along the damper, how far it's compressing this spring basically. The spring itself doesn't compress in SOLIDWORKS, it's not a function we can have. Imagine it is compressing though, but you can see the actual damper itself move in and out. So this rocker is bolted up onto the chassis with a series of bearings that allow for it to absorb the loads as well as pivot smoothly. In the pull rod configuration, you want to think of it as the wheel moves up in this arc, it's going to pull this rod outwards from the car. It's going to pull up on this rod as the wheel moves up. Then, if this rod's being pulled up, it's going to pull on this mount here and force this rocker to turn in a clockwise direction from this orientation. That will in turn push this mount down and compress this damper along its axis. So we can see that if we start moving this rod here. We pull up, it pulls the rod and rotates the rocker, which then compresses the spring downwards. Keep going. And then in the opposite motion, what will happen is this spring will exert a force onto this end of the rocker and try to force it back in the opposite direction, which will in turn turn this counterclockwise, forcing this piece to go there, this mount to go that direction, pulling back on this pull rod and trying to pull the wheel back down towards the ground. And that is your general suspension system. As this compresses out, as the damper extends, it will force the wheel back down towards the ground. A push rod configuration acts exact opposite of this, where this rod will push on the bell crank instead of pulling on it, and thus have to change the orientation of how this is mounted. The general idea is similar. Now, if you're familiar with a production car at all, you would notice that on production cars, this spring is mounted directly onto this wheel assembly here. You don't have this push rod, you don't have the rocker. It's much simpler in a production car where the shock is attached right to the wheel. When the wheel moves up, the shock moves up as well and it compresses. Very simple. The reasoning for doing this is that in our configurations on an FSAE car, we're using really small dampers which can't really bridge this gap. This damper is way too short to reach all the way from the chassis out to this end of the wheel, so we'd have to extend it quite a lot, which is not ideal. This also means that by having the damper mounted further inwards to the car and using this pull rod, we can move our mass closer to the ground and closer to the center of the car, which gives us better handling characteristics. And finally, it lets us play with motion ratios, which is how this piece turns here, change how the damper compresses, which effectively changes the spring rate. A larger motion ratio will change the spring rate just like a lower motion ratio will. So that way we can use softer springs. Softer springs are generally better in this situation just because they absorb bumps a little bit better. You don't want to go too soft because the car will bottom out, but a nice soft spring will allow for great absorption of bumps on the track, keep the car really planted to the ground. So that's the general suspension assembly. Then we'll also move on to showing a push rod configuration here. So this is all the same parts. This assembly is also broken. I can't move it. This is old. So pretend this all functions. It doesn't really though. You have similar components though. This is an upright here, lower control arm, upper control arm, push rod, rocker or bell crank, and then damper. And if you can just imagine the motion here, as the wheel moves up, it will push on this rod, which will force this bell crank to rotate, and that rotation will force this damper to compress. Likewise, in an opposite motion, the damper will want to extend back outwards to exert a force back onto the bell crank, rotate it back in the opposite direction, push down this rod, and force the wheel back down towards the ground. So the same end result as the pull rod configuration, just set up in an opposite manner. They don't perform all that differently. The reasoning for choosing one or the other is more due to packaging constraints. So looking at your system and saying, where can I fit these components in? Certain applications will allow you to fit a push rod system. Certain applications allow a pull rod system to fit better. It all comes down to the packaging constraint, but at the end of the day, the performance between the two of them is the same. So the choice that you make on that, completely based on where you want to place your components. Don't think of it as a performance difference though. So we'll go back to the working assembly here. That is a general rundown of how this all attaches. I should also point out more rod ends here at the pull rod allows it to pivot. Rod end down there again, once again, allows it to pivot. And this damper also has small spherical bearings built into it that allow it to pivot. You do want to keep everything as in plane as you can. You don't want to put rod ends on a huge angle because it will bend them quite easily and cause binding in the system. The forces just won't translate as nicely. So you want to keep things as close to a flat plane as possible. Notice that in this orientation, when this damper moves, these two ends where the spherical bearings are, they don't pivot relative to each other. They stay completely in plane. The damper moves in a straight line in this configuration. That means that our forces are staying on a nice straight plane and not translating all weird. It prevents binding in the system and allows for smoother operation. Same thing here. This pull rod does rotate a little bit, but only a very small amount. This is almost entirely flat relative to this rocker. It keeps the forces in a nice straight plane and prevents anything from binding. The only spot on here where we see something not in plane is where it attaches up to this control arm. Because really, you can't keep this in plane the entire time. This part of it moves too much for that to even be feasible. We keep it close to in plane. Let's just tilt it a little bit. There we go. We keep this close to in plane, but it will rotate more than the rest. Try to minimize it though. You want to keep that as minimized as possible. And so that should give you a general overview of the suspension system. It's all just mirrored over here. But the key thing to take away from this is what your control arms do, what the push rod, rocker, and damper does, and how it all functions together. Getting a good grasp of how this linkage system works and how it all moves the damper based on wheel travel is a very important concept to grasp before you start designing these suspension systems. Pull rod configuration might be a little bit harder to wrap your head around, just because the forces are kind of counterintuitive. But try it out for yourself, put together one of these assemblies. It does take quite a while. It's worth a shot though to get a good idea of how it all works. I guess the final thing here, if we just stop this from moving. All right, these are all locked in place. The last thing to consider here is that this upright can also pivot on its own axis. That allows for steering. This has to pivot for the wheel to steer. In a completed assembly, you would see one last rod connected to this piece here, which connects to your steering rack. When this is pulled in and out by your steering rack, it will pivot the upright. That's what gives your car steering capability. It's not shown in this assembly here, but hopefully you can get an idea of how that all connects together. in a more completed assembly, we could represent that. You have a steering rack in here somewhere. When you turn a steering wheel, it'll pull on this or push on this and turn the upright. That's kind of the last piece to the whole assembly. And that is about it for the major components of the system. Hopefully it all makes sense. If not, shoot someone a question, look it up online, try to figure something out, and good luck for future designs on it.